Hello, it's Keith here, and this is lesson 1 of the multi-platform series of my 68000 assembly programming tutorials. Now, the multi-platform series, the code we look at, it basically will run on any 68000 based system. Today we're looking at a speech synthesizer. This was originally ported from the Z80 to the 68000, and the code we'll be looking at today and in these two lessons will basically work on any 68000 system. All you need to do is write a platform-specific small part that will actually set the volume level according to the wave sample to actually output the sound. But that's not the point of these tutorials. We're actually looking at the processes involved in converting text into speech using a simple speech synthesizer, which, as I say, is ported from these Z80 systems. Now, I do need to say something about that. Usually in my tutorials the code is entirely written by myself, and I always give you the source code and say you're welcome to use it however you want. I'm giving you the source code today. You're welcome from my point of view to use it however you want. However, this has been disassembled from a binary that was distributed, and so I can't claim the original source code, ownership of the original source code. I've made some changes, but legally, you know, it's going to be in very odd, very shady situation, so you use at your own risk. Now, the program itself was distributed as speech. It was called just speech by Superior Software in 1986, and that actually was released for free on an Amstrad Action cover tape on the Z80. But the same program was also actually distributed as the speaker by Xavier in a magazine called Grosset, a French magazine, in 1991. So two people have claimed copyright for this. I don't know what the case is. I don't know if any of those people would still care if you decided to use it, but as I say, I have to just tell you the situation there, so use it at your own risk. Anyway, that's enough talking about that. Let's actually hear the speech synthesizer in action. So it's a very basic software speech synthesis. So it said, I am a Genesis, you are a worm, you will bow to my 68000 superiority, because for some reason I find it quite amusing to make the computer insult us once it has the speech to do so. Now on the screen here you can see we've actually got this text here, which is the original text, give or take, and then we've got this weird text here which has been converted into phonetics. I think it's called phonemes. I know very little about speech synthesis. That is why I had to disassemble someone else's code. But anyway, the part of the code we're looking at today is going to be the part that takes the raw text and processes it into this sort of phonetic version that can then, in the second part, which we'll look at next time, actually play back as a series of 4-bit PCM wave samples, basically, that make up the actual sounds that need to be played to make up those parts of the speech. Anyway, let's go over to the source code and let's see what we've got. So here it is. So this is the source code today. Now, on each system we need some memory. We define basically user RAM on every system, so that we've got the multi-platform function there, and then basically we're defining all of these variables here. So these are all most of them contained as is from the original disassembled source version. I've made some tweaks to save some memory, make things a bit more efficient. One of the things I did is in the original it was storing the string into fixed memory locations, and I've actually changed those so that they're actually combined into a single memory location. So text raw string needs to have enough space for 2 copies of the string that you want to play. Now it gets bigger because of the phonetic conversion, but as I say, just roughly speaking, you need to allocate some memory there. So about 256 bytes or something might be okay. But anyway, so here is the raw strings we're playing here. Now in some cases I've had to fiddle with them a bit to get the names of computers to sound roughly correct, but this is the original text, and you can see it's in lowercase, and we've got quite commas and full stops and things. Now the first stage that the program will need to do is actually convert that to uppercase, and then the second stage will be to convert those uppercase letters via a lookup table into the phonetics that it needs to play back. Now to actually play the string we use this routine, say string from HL. Now the HL was a Z80 register, which is the main sort of addressing register, for which I use A3 on the 68000 systems. So that is the string we want to play back in normal format, and that is actually 0 terminated at this stage. And then we load a speed value from 0 to 15, I think it is, in here, and if we make that a higher number, the pitch will get higher, and the speed will also play back. The pitch is just changed by changing the speed, so it gets faster and higher pitch. So we can do that if we want to mess around, but we'll leave it at the current situation. And let's take a look at this say string routine. Okay, So the first thing that this is doing basically is it's taking the speed in the D0 register here, and it's making some changes to it to convert it to the correct kind of value that the speech playback routines, the wave playback routines, can use as a valid delay in between each loop of the samples. So that's being set up there. And then we're moving the source string into A2 here, and we're loading the buffer for our converted string into A3 here. And we're going to start that with a space, and that's for the matching routines, so that they've got a consistent thing to sort of match. And then what we're doing first of all here is we are copying the source string byte by byte into the destination here. So that's what's happening there. And then while we're doing this, we're also doing another thing, and we're remembering the last character in the string, and we're making sure the string ends with a space and then a character 13. So we need to be character 13 terminated at this point for the other parts of the code. And we've appended a space, and we've put a space at the start as well. The other thing that's very important is we've remembered the last character in the string. Now, the speech synthesizer has a function where if the last character in the string is a full stop, the pitch will be shifted down for the last vowels, I think it is basically. So the pitch goes down to make it sound like the end of a sentence. If there's a question mark at the end, this is a question, then the pitch goes up, you see. So that's why we're remembering the last character here. It's for the actual playback routines later on. So that's just copying the string and remembering that last character. And so what then happens is we run this char fix routine. So let's take a look at this char fix routine. So what this is going to do is mostly it's just converting us to uppercase. So we're checking the range of characters here. If the range is in the uppercase range, then we're just going to leave it alone. Otherwise, we subtract 32, 20 in hexadecimal, and that converts lowercase to uppercase. And then the only other thing we're doing is we're replacing this slash symbol with a space, basically, because that slash symbol has a special function within the phonetics. It creates a special kind of, I think it's a sort of distorted sound it creates, so that has a special purpose, and so that's why we're removing it at this point. Anything else, generally speaking, we're leaving, because to be honest, the playback routines will ignore any characters they don't recognize, so you can put any other weird characters in there if you so wish, and it won't have any negative effect. Okay, so that's what's going on there. So once we've done that, we've now got an uppercase string that is prepended and suffixed with a space, and we've removed any really dodgy characters that we are going to cause us problems. So now what we're going to do is we're going to run this convert to phonetics routine. And so here this is. Now at the start of this, firstly we're storing the string that we want to convert it into this address here. And we are going to basically convert each of the phonetics one at a time here. So this routine is doing the conversion. Now, one other thing I should have said is the convert to phonetics routine is using the memory immediately after the uppercase string. So we're continuing on with that same address, and as I say, the original didn't do that, so I made a bit of an improvement there, but just more efficient memory usage really. So that's what we're going to do. So this translate to phonetics routine is going to basically do the job of converting all of the string into valid phonetics that can be then used to look up wave samples, which we'll see next time. Okay, so what we're doing here is we're checking to see if we've got to the carriage return 13 character here. If we have, then we're done and we just return. We're jumping up to a return command here. Otherwise, what we're doing is we're using phonetic lookup entry, and this will find some kind of match within the phonetic lookup table. I say some kind because the last one is a catch-all match that will match literally a single character, and it will just say, hey, well, I don't know, use the character you're given. So that's pretty straightforward. So this will always find some kind of match, and then we transfer that match into our destination string, and we just keep repeating until we find that character return there, carriage return there. So here is the phonetic lookup entry routine. Okay, so what we're doing here is we're going to basically use a lookup table to do the phonetic conversion. Let's take a peek at that lookup table. Well, here is the actual conversions table here. So we've got David in normal English here, and then we have the equivalent conversion DAY VIHD. So that's the phonetic converted equivalent there. So these are the ones that start with a space here, but we have ones that start with every letter in the alphabet, like age here, AYJ. And the thing to notice here is that we've got the original string a 0 byte and then the converted string and then a 0 byte, and these are in pairs, and then the final one is a catch-all. This one down here is question mark, question mark. Now question mark has a special function. A question mark in the source remembers the character in the source and then puts that character in the destination as well. So question mark simply passes back the original character that was passed to it. But you will see this used in other places along with those slashes that, as I say, have a special playback sound. But you see here there's a question mark in this source string here, and then that question mark is used again in the destination, and that will basically copy the single character from the source to the destination. The 3 here is actually a delay. It changes the playback speed basically. It can increase it or decrease it. It's a signed change there. So that is our lookup table. Now the other thing we've got this set of pointers to the lookup tables. Now these are longs, so they're 32-bit, and these are these are the memory addresses to the various positions in the lookup table. And what these are is so that we know if our characters that we want to try and convert start with an A, then we want to start from this position in the table really, because that's going to have the most accurate matches there. So that is that's what this lookup table is for. So what we're going to do here is basically at this point we're just checking if we've got a valid letter from A to Z here. That's what that is doing. If we haven't, we drop down to here and we either use the space lookup table or the number lookup table here. So that's what we do for non-letters. But if we've got a letter, what we're going to do is we're going to basically change that to an offset within the memory addresses for that lookup table. So what we're doing is we're subtracting A, so that changes us from an A to Z entry to a 0 to 25 entry. We're then multiplying that by 4 because there's 4 bytes for each address in the pointer table, and then we are using that as an offset to that pointer here, and that is the address that we're going to start trying to use for our conversion here. Okay, and then when we want to actually test these conversions, at this point we've got a potential entry. It'll probably be wrong, statistically speaking. We're just looking at the start of the table, so we'll probably have to do this a few times. But what we're going to do is we're going to try this entry, and this will return the carry set if this matches what we wanted to convert, in which case we'll return to the calling routine, because if you remember, the next thing after the lookup is the actual transfer routine. So that is once we've found what we want. Now we'll have a look at this testing routine in a moment, but most times the first test it does, it will fail. It'll have to fail a few times until it finds something that will work. So when we have a failure, what we basically want to do is we want to skip that entry in the table. Now if you remember, there's 2 entries in the table, each of which is 0 terminated, and these are pairs, so a source and a conversion equivalent. And so what we want to do is we want to find 2 0 bytes basically. So we're going to look for a 0 byte, moving along the string until we find one, and then when we find one, we want to skip the first one and then find a second one. So I'm using a dbra command, which actually runs for 0 as well. So if we loaded in the value 2 into our count register here, it would actually find 3 entries, which isn't what we want. So we've loaded it with 2 minus 1. So D4 has been loaded with 1, and it will go down to 0 when it finds the first 0 entry, but then it will find another one and go down. It's only when it goes down to -1 it doesn't jump back. So that is basically skipping over the 2 entries and finding the next entry for the next conversion there. Okay, so it's this phonetic match test that we need to take a peek at now. So what this is going to do is it's going to basically consider our source string and consider our conversion entry in the lookup table. So it's comparing the raw string to the source of the conversion, and then it will use the destination to make the conversion if it matches. So we're comparing the characters here. We've got some special routines for spaces and question marks here. So these just basically move to the next entry here. Now the one special case is, as I say, is when we have a question mark in the conversion string, what we actually want to do is we actually want to get a character from the source string, and we're going to remember that for later on. So that's what we're doing here. We're also just checking if we've actually got to the end of the string already, because obviously that wouldn't make any sense to store that. That's what's happening there. But then for the other things, basically the other characters, what we're doing is we're comparing to the entry within the source string. So A3 is the string we want to convert. D0 contains the value from our conversion table. Now if this doesn't match, then we go to phonetic no match here, and that will basically give up. We're clearing the carry to say that this didn't match. There's no point looking at the rest. We've already found something that didn't match. Otherwise, what we're going to do is we're going to continue. So we're moving to the next entry and we're repeating here. So we're just testing each entry. Now at some point we might find we've got to the end of the source conversion. So we find a 0 byte, and that means we've actually found a match for this entry. In that case, what we're going to do here is we're going to actually walk back to the start of the source string. Now this is a little bit odd what it does. This is one of those kind of cases where the disadvantage of disassembling something from a binary and not writing it yourself is that I don't entirely understand why this does what it does. In some cases I could see what it did and thought I could do better. In other cases I was just like, well, I guess it works, I'll leave it alone. And this is one of those cases. So basically what it's doing is it's skipping back to the start of the string, but it's got this weird conversion thing where it checks the byte 3 characters before the current position, and then it changes the offset in the source string accordingly. So I guess this is related to the length of the comparisons, and so I guess they have a consistent length or something. It seems a little bit strange, that, but as I say, it was like, well, I don't quite understand why it's doing that. I'm going to leave it well alone. So as I say, I've just left it as is. And then what we're doing here is we're setting the carry to tell the calling routine that we have found a successful match. Now you will see at some points within our code here, you've got this valid phonetic test here. Now what this is actually doing is it's checking the byte in the source, and it's checking for a letter or a number here. And so this is again looking at the source string and seeing if the letters it's been given are things that it's going to find within its translation table here. So again, that's just part of the code that's doing that conversion there. But basically, as I say, that phonetic comparison routine will continue until a match is found, because the last match will always match because it's just a single character. And then once we've found the match, we run the transfer entry routine to actually make the conversion. So conversion address is our lookup entry that will do the conversion. Translated string address is the actual source string that we want to convert here. And so what we're doing here is we're loading in a character from our conversion into D0. If it's a question mark, we're going to use that character that we copied in from the source string. Otherwise, what we're doing is we're running it through this vowel switcher, which is to do with changing the pitch at the end of the sentence. But basically, we're then storing the character from the conversion into our destination string, which is still at A3. So we're adding this to the end of the previous uppercase string, and this is now the phonetic conversion that we'll use for to decide which samples to use. So that's what's happening there. We're just going through the string until we're basically done, and we carry on until we get to the end of the conversion, which is a 0 byte, and so at that point we'll be finished. Now the vowel switcher here is basically seeing if the current letter is a vowel, and if it is, it runs this HL switcher routine. Now what this does is it actually looks for the memory address of the last 2 vowels in the sentence, and these are the points that the pitch will change for a question or a full stop. The pitch goes up for a question, down for a full stop, and so we're remembering the address of those two here, and we're storing them in HL switch address 2 and HL switch address 1, and we use these later on to see if we're at those character positions that we want to change the pitch. That is what that is doing there. So that is that's remembering that for the wave playback routines, and as I say, we will see those next time. So at that point, basically this routine will be completed. Now I've put a memdump in the code here so that we could actually see what was going on. So if we run this here, you can see you can see for debugging purposes, you can see the source and the equivalent converted string there. Obviously, if you were using this in your code, you'd rem that out. But following on from that, we basically run the speech routines here, and those are what we're going to take a look at next time. So if you like what you've seen, please like and subscribe so you see that second part. The speech.asm, as I say, you can download from my website, and you're welcome to use it from my point of view in any way you want. But as I say, it is someone else's code. Now, there were a few parts of this code that I didn't quite understand, and not so much this time, but in the wave playback routines, I made a lot of optimizations. But one thing that I think it's important to sort of say at this point is You've got to bear in mind that in these days, using modern tools and, you know, as a hobbyist, you sort of have much more ability and much more time to actually spend on these. I have a hunch that the original version was probably sold in one of these magazines, you know, for $5 or something. So probably didn't make a whole lot of money in its day, and it was eventually released free on a magazine. So it was probably developed under extreme time constraints, and also, you've got to bear in mind these old tools that they used to use. Recovering from a crash, if you were loading your assembler from a disk, you know, you could easily be spending 10 minutes before you're running your code again. So it's not surprising that it's a lot easier for us to optimize our code these days. And in some cases, in the example today, there was actually a bug in the original, as far as I could tell, that it was using the address of the space and the numbers lookup table. It was using a pointer to the address and then treating it as the address itself, which seems to me to be an obvious bug. But again, you know, these kind of things, easy mistakes to make when you're under considerable time constraints and things. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.